Now we'll solve the same question using the concept of work, energy. Okay, not that was the chapter name of the chapter. Using the concept of conservation of mechanical energy. Something very important that I didn't mention in the last solution is the frame in which we are solving this question. So this is observer here. He is standing on the ground. The ground is a moving frame, right? And therefore the frame is inertial. Okay. And the ball is being dropped from some height. Now, how do we come to the assumption that the ball is dropped? We already have discussed that in the previous solution. And like I said in the first one, that we will validate that our assumption is right here and it matches the given description. After we discuss all the methods, we have close to 3 to 5 methods. This is the second one. Once we complete all the methods, the last one being the graphical method, we'll then validate our assumption. Okay. So the ball is dropped from point O, where the corresponding velocity is VO and the position is SO. Ball reaches, so this is direction of motion like this, right? For the direction of motion. Corresponding velocity at A is VA, position is SA, and the change in displacement here is SOA. Likewise, over here is SAB, right? Now let's quickly understand what is conservation of mechanical energy theorem. See, I think when you go through the solutions of the numericals in the chapter work, energy, power, you will have very detailed analysis of what is conservation, what is mechanical energy, what does it mean when we say conservation of mechanical energy, what is initial position, what is final position, what is not the path taken, so on and so forth. It goes on and on. There are lots of things that we have discussed in multiple concepts in many different questions. Okay, so I'm assuming that you're here for the first time and you haven't discussed, you haven't learned things in work, energy, power, because you are right now in a motion in a straight line. But you just can't, apply the theorem and then use an equation and then do the question. No, you need some of the very basic things associated with that concept. So now I'll take you through those concepts, which starts from the definition of a conservative force. The conservative force is one for which the work done depends only on the initial and the final position and not on the path taken. Now, I do understand that some of us here might be finding it difficult to follow and make sense out of this phrase, on the path taken. Now, if we go into that, it's going to be, it's this already, this we have deviated a lot from the chapter. This will go even beyond that. Okay. Now, when such a conservative force is acting, the total mechanical energy of the system, which is kinetic energy plus potential energy, remains constant. System, very important, system. Another condition that should be satisfied here is that there should be no non-conservative forces like friction or air resistance acting on the system. So when the system is acted only upon conservative forces, the total mechanical energy, which is the sum of kinetic energy and potential energy, remains conserved. Now, what's the example of a conservative force? Gravity. Gravity is a conservative force. This means as an object falls under gravity. Familiar with this? Where did you see this? Exactly, as in the question. its potential energy decreases and its kinetic energy increases such that the total mechanical energy, which is the sum of kinetic and potential energy, remains a constant. Okay? And yes, please do make notes along with me. At least make a quick note of what's given in the bold, which is highlighted in colors. That would be more than enough for your exam point of view. Easy for your revision as well. So what is mechanical energy conservation theorem? It says that in a system where only conservative forces are doing work, for instance, gravity, the total mechanical energy being the sum of kinetic energy and potential energy, half mv square plus mgh, is a constant. This means that energy may transform between kinetic energy and potential energy, but their sum always stays unchanged. Okay? Sorry, we need to add something here. Okay, sorry, it was already here. Now, while we discuss potential energy, there's something very important, what we call as the reference height. So the expression for potential energy, which is mgh, contains h, and this h is arbitrary. It varies. It you can choose any height as a reference. Now, why is a reference height required here? Because potential energy due to gravity is relative. It is not absolute. So the formula PE is equal to mgh depends on how you define the height h, and that in turn depends on where you place your reference level. I'll give you a visual example and things will become very clear to you. In this case, the level at which you define gravitational potential energy is equal to 0 is what we call as the reference height. This level is arbitrary. You can choose any, not just these three, you can choose any level which is convenient to you. When I say convenient, I mean ease of calculation. So you can either consider the ground to be the reference, or the starting point O to be the reference, or the lowest point like B. Or maybe any intermediary point between O, A, and B can be considered as a reference height. Okay. If, say, for example, I have written here, well, I don't want to go this in detail. So I've given you one case, which is case one, where we assume point O as the reference. What I want to do is, once you have followed this solution clearly, and after you explain this to yourself, if you feel that you are confident, I would suggest that you do case number 2, wherein case 2 would be reference height is point A. And one more time, case 3, where the reference point is point B. Okay. Now, if you're following these solutions in a structured manner, what I would suggest is you please make sure that you definitely go through case 2 and case 3. Try finding out. And if you find anything difficult in that, write to me. I'll be more than happy to reply back. Okay. Now, when O is the top point, which means where the body starts, where the body is initially dropped from, A is some point below O, and B is 80 meters further down from A. So when we consider O, the potential energy is the reference displacement is 0, height is 0, and the potential energy is therefore m into g into 0, which is 0. When A is some point below, say minus 45 meter, which is actually the answer here, the potential energy would be minus mg into 45. B is minus 125 meter, again because it is 80 meters down, potential energy is minus mg into 125. you will get negative potential energy here in both these cases, but the differences would still be valid. Which difference are we talking about? Mg into H2 minus H1. Now, this will hold true no matter which height do you choose as a reference. Be point O, point A, or point P, or for that matter, any other point. Okay? Now, if this much makes sense, let us now apply this law of conservation of mechanical energy in this problem. So this is the condition we have. Ball is dropped from O, reaches A to B, and then ground. We have the corresponding parameters as well. Now what I'll do is, I'll summarize this diagram like this. What's happening here? Object is falling from O to A and then from A to B. Okay. I'll choose O as the reference. I'll choose O as the reference and the corresponding velocities and potential energy as VO, mgh half mv square. To be more precise, well, actually to be precise, mgh0 half mvo 0. mgha half mva square, vb, mghb and half mvb square. The corresponding displacements being SOA and SAB. This should be OA, my bad. SOA. Okay. And the first part of this, we will discuss only the motion along OA. And the reference I've considered here is a line passing through O. Okay. So when the reference is kept at O, what is height of O? Height of O overlaps with the reference, and therefore this height is actually equal to 0. And since it is dropped, velocity of O is equal to 0, and therefore kinetic energy will also be equal to 0. As the body travels down distance HA, or HA, which actually is equal to displacement of along the path OA, SOA, the body reaches A with the corresponding velocities VA, the potential energy is mgha, and the corresponding kinetic energy is half mva square. All right. Now, when we say that the mechanical energy is conserved, it means, now this is actually the point where the solution starts, right? So potential energy at O plus kinetic energy at O should be equal to potential energy at A plus kinetic energy at A. Why? Because this motion is taking place only under the force of gravity, which is a conservative force, and therefore mechanical energy remains conserved. Now, what is kinetic potential energy here? This mgh is equal to 0. Why? Because it is overlapping with the reference line. It is in fact on the reference line. Since it is dropped from rest, VO is equal to 0. VO is equal to 0, and therefore half mv square is also equal to 0. So these two phrases become 0. Now, potential energy at A is equal to mg into HA, but this is actually minus HA. Why? Because this is the reference axis. This is height is equal to 0. Any reference made with the heights lying down on this side would be negative, and anything lying on the up side of this would be positive, right? So lying on the top and lying on the bottom would be positive and negative. Please make sure you make a note of this as well, because this will help you a lot while you do case 2 and case 3 on your own. Okay. So since both of them are equal to 0, we can therefore write that 0 plus 0 is minus mgha plus half mv square. Transposing to the LHS, what we get is mgha is equal to half mvb square. Or in other words, cancelling m by m is 1. So g into ha, which is 10 into ha, is equal to 2. 2 is equal to vb square. Okay. So what did we do so far? The body was falling from O to A and then from A to B. When we applied conservation of mechanical energy along the path OA, along the path OA, along the path OA, we got a mathematical equation which says 20 HA is equal to VA square. Right? Oh, wait. Did I make a mistake here? My bad. My bad. Oh, this is not VP square. This is VA square. Apologies. This is not VP square. This is not VP square again. This is VA square. VA square. VA square. Sorry. Okay. Now what we'll do is we'll do the same question from A to B, right? The same theorem applied from A to B. So conservation of mechanical energy from A to B. Okay. So mechanical energy at A should be equal to mechanical energy at B. Why? Because the only force acting here is the force of gravity, which is a conservative force, and therefore mechanical energy remains conserved. Which gives us mechanical energy at A, which is the sum of potential energy at A and kinetic energy at A, is equal to mechanical energy at B, which is the sum of potential energy at B and kinetic energy at B. Now, as was the case with height in A, we'll have to define that height with respect to B as well. Now, we know that mgha is minus ha and mghb is actually minus hb. To be more clear, to be more accurate here, what we need to understand is this ha is actually SOA and this SB is actually SOP and not SOA. Yes. Now we are in confusion. Oh, we already were. but yes, now we are in deeper confusion. So I have drawn a separate diagram. Maybe once you draw this along with me, things will become, they will resolve better. So this is O, the reference line. This is A, the point where the question is mentioned. And then we have B. From O to A, this is HOA. And what is HOA? HOA is actually equal to displacement from O to A. Similarly, from A to B, we have HAB minus HAB. Why? Because it is lying below the reference axis. But the position of B is actually HOB and not HAB. So what is the position that we're trying to find? It is every time with respect to the reference. And the reference is O, not A. So the height of the potential energy at B is not dependent on AB. It is rather dependent on OB. It is dependent on OB. And what is OB? The sum of SOA and sum of SAB. Does that make sense? So say if it was 10 meter and this was 20 meter, then the HOB would be equal to minus 30 meters. Does that make sense? Right? So this would be equal to minus HOA plus minus AT. Why minus AT? Because it is given in the question that the body travels from A to B, the body travels 80 meters. Okay? Right. Now let's continue with the arithmetic part. So minus HOA minus HOB. HOB is minus HOA minus 80. So in this equation, we have terms like this MgHOA. This is minus, sorry, this is actually the product, right? So minus MgHOA minus MgHOA is equal to 0, right? M by M is 1, M by M is 1. So we only have 3 terms. VA squared by 2, G minus G into 80. My bad, you don't have M here. VB squared by 2, which gives us minus G80 becomes 80G, transposing to the left. VB square minus VA square by 2. 80 times 2 is 160. 160 times G10 is 1600 is equal to VB square minus VA square. Now, when the body is moving along AB, so while we consider motion along the path AB, apply equations of motion V is equal to U plus 80. V is the final velocity, which is VB. U is the initial velocity, which is VA. And therefore, VB is equal to VA plus 80. Since the body is moving along the direction of motion, since the movie is moving along the initial direction of motion, and since the acceleration is acting along the same direction, acceleration here is equal to plus G. Right? And since the motion is taking place for 2 seconds, TAB will therefore be equal to 2 seconds. Therefore, this becomes 10 into 2, which is equal to 20. So VB is equal to VA plus 20. Or in other words, now we have 2 equations. VB is equal to VA plus 20 and VB square minus VA square is equal to 1600. Plugging in VA plus 20 into VB, this becomes VA plus 20 the whole square minus VA square is equal to 1600. A plus B the whole square, A square plus B square plus 2AB, 2 into 20 is 40, 40 VA. And VA square minus VA square is 0. 400, 1600 minus 400 is 1200. 1200 by 40 is 30, and therefore VA is equal to 30 and VB is equal to 50. Now, VB doesn't matter here actually. When VA is 30, we can go back to our first part, where we derived that VA square is equal to 2 times 10 times HA. This VA is now equals 30. So VA square is 30 times 30. HA, we don't know. 2 into 10 is 20. So HA is equal to 30 into 30, 900 by 20. 900 by 20, which is 45. Yes, lengthy, definitely lengthy. And so this is actually a very long way of coming in the solution. But why are we doing this? To make sure that we understand the concept of work and the concept of conservation of mechanical energy, and most importantly, to make sure that we are in a state of preparation where our confidence levels are high. Why are our confidence levels high? Because we are able to solve one question using multiple methods and connecting multiple chapters to one question. Okay? So that gives you a command over your subject. Right? Now we're not done yet. We have to solve the same question using another concept in the chapter work energy power, which is work energy theorem. Not conservation of mechanical energy, work energy theorem. So moving on ahead, solution using work energy theorem.